The Signum Function. Welcome, everyone. Today, we are going to introduce a very interesting and specialized tool in mathematics known as the Signum Function. Now, if you look at the title, you'll see the name Signum. This term actually comes from the Latin word for sign. This is a great hint for what the function does. Essentially, the sign's purpose is to look at any real number and tell us its sign, meaning it tells us whether a number is positive, negative, or exactly zero. The most important thing to remember right at the start is that this function doesn't care about the magnitude or the actual size of the number. It doesn't matter if the number is 5 or 5 million. The Signum function only cares about whether that number is above, below, or at zero. In the next slide, we will look at the formal mathematical way to write this rule down. Formal definition. Now that we understand the basic concept of the Signum function from our previous slide, that it's essentially a tool to extract the sign of a number, let's look at its formal definition. We represent the Signum function as f, mapping from the set of all real numbers to the set of all real numbers. You'll notice that we define this as a piecewise function. Now, don't let that term intimidate you. It simply means that we don't have one single rule for every number. Instead, the rule we use to find the output changes depending on which value of x we plug into the function. Let's break down these specific rules. First, if our input x is greater than 0, the output is always 1. Second, if our input x is exactly equal to 0, the output is 0. And finally, if our input x is less predefined as less than 0, the output is negative 1. To put this all together in a single mathematical expression, we write f of x equals a large bracket, where we list our three cases. 1 if x is greater than 0, 0 if x equals 0, and negative 1 if x is less than 0. As we will see in the next slide, there is actually another clever way to write this using absolute values, but for now, just focus on this three-part rule. Alternative mathematical representation. Now that we have established the piecewise definition of the function, I want to show you something very interesting. Apart from that piecewise definition we just looked at, the Signum function can also be expressed using the modulus or absolute value function. For any value of x that is not 0, the function can be written as f of x equals the absolute value of x, all divided by x, provided that x is not equal to 0. I know that might look a bit different from the definition on the previous slide, so let's break it down step by step to understand why this mathematical shortcut works perfectly. Step 1, let's take a positive number, for example, x equals 5. The absolute value of 5 is simply 5. When we plug this into our fraction, we get 5 divided by 5, which equals 1. This matches our rule for positive numbers. Step 2, now let's try a negative number, like x equals negative 5. The absolute value of negative 5 is 5. When we divide that by our original x, which is negative 5, we get 5 divided by negative 5, which results in negative 1. This matches our rule for negative numbers. Finally, step 3, we must address the number 0. As you know, division by 0 is undefined in mathematics. Therefore, we cannot use this fraction method when x is 0, so we must explicitly define f of 0 as 0, just as we saw in our formal definition. This leads us directly into our next slide, where we will look at the domain and range of this function. Domain and range. Now that we have seen the formal definition and the different ways to represent the function, let's look at something fundamental to any mathematical function: its domain and its range. Understanding the set of possible inputs and outputs is crucial for any function you will encounter in your studies. First, let's talk about the domain. The domain refers to every possible value that we are allowed to plug into our function. In the case of the Signum function, there are no restrictions. The function accepts any real number as an input. Whether it is a massive positive number, a tiny negative fraction, or exactly 0, the function can handle it. Therefore, we say the domain is the set of all real numbers, which we denote by the symbol r. Next, let's look at the range. While the domain is wide open, the range is much more restricted. The range refers to the set of all possible outputs we get after applying the function. As we discussed in the previous slides, regardless of how large or small your input value is, the output can only ever be one of three specific numbers: -1, 0, or 1. Because the output doesn't flow through all numbers but jumps specifically between these three, we say the range is the discrete set containing -1, 0, and 1. To help you visualize this, in our next slide, we will see how this limited range works in a real-world scenario involving an elevator sensor. Real-world example: a simple direction indicator. Now that we have covered the formal definition and the mathematical properties like domain and range, let's step away from the abstract numbers and see how this function actually works in a practical, real-world scenario. Imagine you are looking at the software for an automated elevator system. Suppose there is a sensor installed that doesn't care about how fast the elevator is going, but only needs to report the direction of movement relative to a fixed floor. Let's look at our scenario. The sensor is programmed using the Signum function. If the elevator is moving up, the sensor outputs a 1. If the elevator is stationary or stopped, the sensor outputs a 0. And if the elevator is moving down, the sensor outputs a -1. To make this even clearer, let's walk through a step-by-step application using actual velocity values. First, case A. Suppose the elevator is moving upward at a velocity, which we will call v, of 2.5 meters per second. Since 2.5 is greater than 0, the Signum function of 2.5 equals 1. Next, case B. Imagine the elevator has reached the lobby and is stopped, so the velocity, v, is exactly 0 meters per second. Since v equals 0, the Signum function of 0 equals 0. Finally, case C. Suppose the elevator is moving downward at a velocity, v, of -1.2 meters per second. Since -1.2 is less than 0, the Signum function of -1.2 equals -1. As you can see, the magnitude of the speed doesn't change the output, only the direction matters. Now, before we wrap up with our final summary, let's look at some common pitfalls to avoid when working with this function. Common mistakes to avoid. Now, before we wrap up our lesson with the final summary, I want to pause and discuss some common pitfalls. When you are first studying the Signum function, it is very easy to fall into a few specific traps, so let's make sure we clear these up now. First, a very common error is confusing the Signum function with the modulus function. It is easy to see why they both involve the absolute value, but they serve different purposes. Remember, the modulus function, or the absolute value of x, returns the actual distance from 0, which is always a non-negative number. The Signum function, however, ignores that distance and only cares about the sign, meaning the output is strictly limited to 1, 0, or -1. Second, watch out for errors regarding the range. Because we discussed earlier that the domain is the set of all real numbers, some students mistakenly assume that the range must also be all real numbers. Don't let that happen. Always remind yourself that no matter what number you plug in, the output is restricted to just that small set of three specific values: -1, 0, and 1. Finally, be very careful when using the alternative formula we looked at on slide 3, where we express the function as the absolute value of x divided by x. A common mistake is forgetting that this specific formula is invalid when x equals 0, because you cannot divide by 0. Whenever you use this algebraic representation, you must explicitly state that for the case where x equals 0, the function equals 0. Keep these distinctions in mind, and you'll have a much stronger grasp of the concept as we move into our final key takeaways. Key takeaways. All right, we have reached the end of our lesson, so let's bring everything together with a quick summary of the key takeaways. First and foremost, remember that the primary purpose of the Signum function is simply to identify the sign of any real number, telling us whether it is positive, negative, or 0. To recap the formal definition we looked at earlier, The function f of x is defined as a piecewise function where the output is 1 if x is greater than 0, the output is 0 if x is equal to 0, and the output is -1 if x is less than 0. As we discussed in our alternative representation slide, you can also express this using the modulus function. For any x that is not equal to 0, f of x equals the absolute value of x, divided by x. Just keep in mind that we must handle the 0 case separately to avoid division by 0. Finally, let's solidify the properties of this function. The domain is the set of all real numbers, which we denote as R. However, the range is much more restricted. The output can only ever be one of 3 specific values, which we write as the set containing -1, 0, and 1. I hope this summary helps reinforce what we've covered today. Keep practicing, and I'll see you in the next lesson.